Hi, this is Mark. In this video, I'm going to derive the circumference of a circle. To start out, just construct a circle, and you let radius equal to 1. And when you construct a circle, you can connect it into four equal dimensional parts. So if we're considering this we're going to consider this first quadrant right here. And for this case, we're going to let xi equal I over n squared, where I equals 1, 2, to n squared. So in this case, if I equals n squared, then xi equals n squared over n squared equals 1, which is equal to radius, r. Satisfies the radius. So if we're going to let the radius be 1, what we essentially did is we're going to have parts. So we break it into n segments, and each of the segments, or the distance we can call delta xi. And delta xi here is equal to 1 over n squared. It's basically the difference between delta x2 and delta x1, delta x3 and delta x2. We get 1 over n squared. So we make it that way, and then we have the difference. This distance is going to be 1 minus delta xi, which essentially this distance is equal to or in this case, this is 1 minus xi. So xi would be 1 over n squared, 2 over n squared. So, it's just going to keep getting smaller and progress all the way to this point in the middle. And essentially, we're just focusing on what we're actually doing right here is we're constructing n square segments. So if we project this line up here and construct, so there's 1, 2, 8 segments. So if we do 8 square segments and steps, we're basically going to represent this. So what you do is you can draw a projection here when we have the line segment intersecting right here, and it's projecting to this endpoint. So what we find is there's going to be 2 triangles. What we have the original triangle, initial, and this is going to be 1 minus xi. This distance right here we can call, so that distance we can represent it as yi. And then this distance right here we know is 1. This is a radius. And then we have another triangle. And then this is just going to be delta xi. This distance we can call li. This is what we want to find. And then this distance right here is this yi. So what we notice you just continue. You create the next projection, and we have the line segment going down. And what we find is for the next triangle, so we have y2 minus y1. So when you're constructing the length, so let's say this is y1, y2. Well, if you continue, what we find is the distance between here we can let as delta xi. So in fact, we can let delta, so essentially the first distance, so we can delta y 1 equals y1. And then we can say for I greater than 1, we have delta yi. So essentially, in this case, delta y2, so we have delta yi plus 1 equals, okay, so in this case, or delta y2 equals to y, in this case I, minus y I minus 1. Or we could just say delta y I plus 1 equals yi. And this is like, for instance, if you start with I equals 1, this is be like, if we start y equals 1, this would be delta y2 equals y2 minus y1, which is what we have right here in this case. So if we constrain this for I greater than or equal to 1, we can have that relation. So essentially, this is going to be part of the iterative formula. What we're going to do right here is we're going to use the Pythagorean theorem. So this states if you have a triangle, if A, B, C, so we have A squared plus B squared equals C squared. And I'm going to show in another video how to actually derive the Pythagoras theorem. It's pretty interesting. There's multiple ways you can derive it. But given this relation, we have, if we go back to the triangle, we're going to use, we can construct it again. If we start right here, this is 1 minus xi. We have, call this delta yi. And then we call this 1. And then we have the other triangle. This is this delta xi. We know that's 1 over n squared. We know that this is li, what we're finding, and this is, that's delta y. This is essentially equal to just yi. So for this triangle right here, we have 1 minus xi squared plus yi squared equals 1 squared. So therefore yi squared is just 1 minus xi squared. Or we have yi is the square root of 1 minus xi squared. If we deconstruct this, we have square root of 1 minus 2xi plus xi squared. And then if we essentially find that the 1's cancel, and then the negative transfers over here, negative times negative is positive, and then that becomes negative. So we're left with positive 2xi minus xi squared. Trying to think right here. So essentially, so this equates to xi 2 minus xi and we know two minus xi is always greater than 0 since xi is less than 1 for all I. So let's see if we did that right. 2xi minus xi squared. xi squared is very small. So therefore, this we know is greater than 0. So given that relationship, we solve for yi, and the key here is delta yi equals, now we're going to take just xi plus 1, 2 minus xi plus 1, minus xi, 2 minus xi, and close. So creating the relation, so iteration 1, we already know for iteration 1, we constrain it to, we have delta y1 equals y1. But then when you get to delta y2, so this is like the base case. We can call this iteration 0. This is base case. And then for beyond here is like, we do iteration 1. We know that delta y, 1 plus 1 is 2. So next one. And then this is just, we know that this is this y2 minus y1. And you keep going and so forth. So that's part of the iteration. And then we have the other triangle. So for this case, use the Pythagorean theorem again. We have, in this case, so we're going to use, so this is 1 over n squared, or equals to x, we can just call this x1, or delta x1. So what we know is delta x1 equals delta x2 equals delta xn. So it doesn't matter for that case. And we know this li, and then this is delta yi. So what we know here is delta xi squared plus delta yi squared equals li squared, or li is just equal to the square root of delta xi squared plus delta yi squared. So this is the initial relationship, and we can let's just try to solve, if we solve the initial case. This is the equation. So basically, if we take the circumference, basically is going to be approximately equal. So we have the summation I equals 1 to n of li, and this is going to be approximately equal to pi. It's going to be 4 times this, and that's going to be approximately equal to 2 pi. So basically, for the iteration, let's just suppose we're gonna let n equals 3. So notice the interesting thing about this is as n approaches infinity, c approaches 2 pi. Of course, the error, we know the error approaches 0. So it gets more and more approximate. We get a better approximation. But we're just going to let n equals 3, which is quite small. So therefore, so really n squared is 9. 3 times 3 is 9. So therefore, we can say that we know that delta x1 equals delta x2 equals delta xn. We know that this is 1 over 9. Okay, starting that, for instance, we have x1. We know this is 1 over 9. x2 is 2 over 9, so forth. So if x1 is this, we're going to start iteration 1. If x1 equals 1/9, then Then we have 1 minus x1 equals, we have 9 ninths minus 1 ninth is 8 ninths. So basically that's the critical point. So when we were constructing the original triangle, what we're going to have is 8 ninths. And then right here, we have y1. Right here, we know this is 1. So therefore, y1 equals the square root we know is 1 minus 8 ninths squared. And then this is equal to the square root of 81 over 81 minus 64 over 81. And this is going to be equal to the square root of, I think, 17 divided by 9. So square root of 17 over 9 is y. So now we're connecting the other triangle. So we have root 17 over 9. This is just 1 ninth. This is L1. So with this triangle, we have L1 squared equals 1 9 squared plus root 17 over 9 squared. Or we just say L1 equals the square root. In this case, we have 81 over 81, or 1 over 81 plus 17 over 81. And that's just the square root of 18 over 81, which is the square root of 9 times 2 over 81. And we can take a 9 out because square root of 9 is 3. So 3 root 2 over 9. And essentially, this is just 3 over 9 is 1/3 root 2 over 3. And I believe this is approximately 0.4 7 something. I didn't use my calculator, somewhere around here. And it's a close, so what we notice a few things. This is just iteration 1. So if we take, if we're going to take, we have L1 is this root 2 over 3. And then we're going to solve L2, L3, and you keep going all the way to L9, and you take the sum. You should get approximately, I think, 1.57 ... approximately equal to pi over 2. And then if you take 4 times this, because we only went from a half, we're essentially, we only took care of this region. So if you do, of course, pi over 2 times 4 gives you, so you get approximately equal to 2 pi. If you take the whole thing, because this is a redundant, doing it this way, it's the same. It's just this direction, you do that direction, and then you do the other direction. So it's the same process. You just take this as your length, this is your next length, and then this is, your length. So the key here, though, is you notice that the sum of, we're going to use logic. So the sum, so we know that L1 is going to be greater than L2, greater than L9. To prove this, hurry up, I need to hurry up. So to show this, if you draw a circle, you draw a line, this is y equals x. In this quadrant right here, we have, suppose we have this is y, this is x, or delta y, this is delta x. In this quadrant, we have delta y greater than delta x. This is delta y equals delta x. And over here we have delta x, delta y less than delta x. So because of that, what we're finding is, well, essentially, the length. So you have the length segments. So delta x, we know delta x1 equals delta x2 These stay the same, they're constant. But yet delta y gets smaller. Delta yn is much smaller than delta y1. So therefore, that implies L1 is going to be greater than L9. So we start with like 0.47, and then we're going to have plus for the next one, the next segment is going to range from 0, or the next number. So the range for the next number is going to be 0 to 0.47, not included. So anywhere within this range, 0 to 0.47 dot, this could be in here. And then the next one is going to be somewhere over here, and then you have over here. And as you keep going, well, you notice once you get to L9, it's converging. So we're converging to that point. So it's a formula that's useful to get to converge to the circumference quite fast. In this case, I use n equals 3, but there's many different ways to derive the circumference. This is just one way, and yeah, I hope you enjoyed it.